Hello, everybody. Let's see you again. And let's start our lecture number 4. Okay? So, let's go. Gradually, field potentiometers grew in popularity over wire-bound types. Why? Because of higher resolution and a better resistance against moisture. However, one important disadvantage still remains, where due to the sliding contact of the wiper. And to get around this drawback, contact-free potentiometers have been developed. In the design, the slider has been replaced by a floating electrode. And the resistance track acts as a counter electrode on the capacitor. Obviously, wear is minimized in this way. The basic construction of potentiometers with capacitive readout is shown in this slide, namely on figure A, on the top part of this slide. Here you can see the floating wiper as a yellow color here, which is capacitively coupled to the resistance track and a conductive return track. Resistance, more blue color, and a light blue color return track. A voltage V is connected across the resistance track and the return track and linked to the interference phase circuit. In figure B on the bottom of the slide, you may see the electric circuit model of the sensor and the simple readout circuit. Here, C1 is the capacitance between the resistance track and the wiper. C2 is the capacitance between the return track and the wiper. And C3 is the stray capacitance between wiper and ground. The inverting input of the operational amplifier is virtually at ground potential. So the voltage across the cable impedance Z sub C, yes, you can see here, must be equal to 0. And this makes the transfer of the device independent of the cable impedance. When the stray capacitance C3, here in this one, is small compared with C1 and C2, the voltage transfer of this circuit is given by this expression on the left side. And you can find here on the first equation. Here we can find the CW equals C1 plus C2. And RP is a parallel resistance of two parts of the potentiometer, right? Okay, so the letter varies with the wiper position. Its maximum value occurs when the wiper is in the center position of the potentiometer and equal R over 4. Why? Because we have 4 elements. The transfer function shows a first-order law path behavior, characterized by the time constant RT times CW. Since the wiper capacitance CW is almost constant, the sensor time constant varies with the wiper position. Halfway through the electrical stroke, the system has the lowest voltage. And for low frequencies of the source, voltage, the output voltage is directly proportional to VR of our potentiometer, hence proportional to the displacement of the pipette. And the low frequency gain of the interface circuit amounts CW over C4 and can be given a specified value by a proper choice, namely C4. But we should notice that the feedback capacity C4 should be shunted by a resistor to prevent the operational amplifier from running into saturation due to integration of its offset voltage and bias current. Together with C4, this resistance introduces another time constant. So the associated cutoff frequency should be chosen well above the frequency of the voltage source. Do you agree with me? Nice. Similar to the conventional types of nonlinearity, of the constant free potentiometer is determined by the inhomogeneity of the resistance track and is therefore not much better than the traditional type. However, the transfer characteristic is somewhat smooth due to the expansion of the floating wiper. Why? Because small location irregularities are averaged out. Okay, let's go. Contrary to this contact-free solution, using capacitive coupling, also film potentiometers with resistive polymer exist. And if you can see for this figure, you found this resistive polymer, which use pressure to make contact between the wiper and the resistance track. In this case, the wiper consists of a long conductive track which extends to the full length of the resistance track. Pressure applied by touch, by another say, through a human finger or mechanical device, will make contact between wiper and track at certain spots. These devices also avoid the sliding friction normally associated with mechanical wipers. Potentiometric sensors are very popular devices because of the relatively low price and easy interface. Moreover, evidently linear and angular potentiometers can be used as sensors for linear displacement and angle of rotation, respectively. For this application, the construction element of which the displacement or rotation should be measured is mechanically coupled to the wiper. If the range of movement does not match that of the potentiometer, a mechanical transmission can be inserted too. However, this might introduce additional backlash and friction, which reduces the accuracy of measurement. But proper alignment of object and sensor is extremely important here. So, potentiometers are widely used in all kinds of mechatronic systems to obtain information about angular position of rotating parts. When small dimensions should be combined with a high resolution, potentiometers may be preferred over the popular optical encoder. For example, controlling a multi-figured robotic hand requires several angular position sensors located at the joint of the fingers. Right? Right. Potentiometers have been considered as one of the possibilities to achieve this goal. This figure shows the potentiometer in combination with an elastic element. I used to measure joint angle alpha and beta, from which follows the touch force exerted by fingertip on the object. A particular application of a potentiometric sensing device is an angular sensor for knee rotation. Two non-elastic wires are positioned along the leg in parallel to the plane of rotation. At one end of the wires are connected to each other, and both other ends are connected to the sliders of the two potentiometers. Spring keeps the wire stretched. And then, on bending, the free ends show a relative displacement related to the angle of rotation. In this case, the potentiometers from a Wheatstone bridge show only the position difference of the wire ends in measurement. The resolution of the measurement is better than 0.1 degree over a range of 100 degrees. The use of potentiometers is not restricted to the measurement of linear and angular displacement. They can also be used for the measurement of acceleration, force, pressure, and level. In these cases, the measurement is transferred to a displacement by a proper mechanical construction. And combined with a spring, a potentiometer can act as a force sensor. With a seismic mass fixed to the slider, the construction is sensitive to acceleration. Potentiometric accelerometers are available for ranges up to 10 G. In accuracy, usually around 2% full scale. And a lateral sensitivity, usually less than 1%. Another say 1% of the sensitivity along the main axis. So, potentiometers find also application in gyroscopes with spinning rotor. When rotating, the axis of the rotor tends to maintain its original position, and hence making an angle with the center head causing in proportion to the angular velocity. Gyroscopes are available in which two angles, roll and pitch, are measured by building potentiometer. Another application is the measurement of level. For this purpose, potentiometers of the type shown in this figure C. In case of a liquid, and one end of the flexible cable is connected to a floor, and the other end wound on a drum. When the level is raising or lowering, the drum winds or unwinds, and rotational potentiometer measures the rotation of the drum. In case of a granular material, the measurement is usually performed intermittently. What it means? It means a weight on a flexible cable drops down until it reaches the top level of material. The sudden change in the cable tangent marks the distance over which the cable has been unrolled. A potentiometer-like sensor for measuring tilt. Yeah, indeed. And also not a potentiometer in the usual sense. It functions in a similar way. The resistive material is an electrolytic solution residing in a micromachine cavity. And the three electrodes are fixed on the board, but two at both ends of the cavity and one in the middle. In horizontal position, the resistances between the middle electrode and the both end electrodes are equal. But when tilted, the resistance ratio varies according to the angle of rotation. The potentiometric structure makes part of the stone bridge, which is AC driven to prevent electrolysis. A resolution for better than 1% over an inclination range of plus minus 60 degrees usually achieved. Strain gauges a wire or film resistor deposited on a thin, flexible carrier material. The wire or film is very thin, so it can easily be stressed. Usually strain is limited about 10 in power minus 3. And in 1843, in his first publication on the now well-known bridge circuit, Wheatstone mentioned that the resistance of the wire changes due to the mechanical strength. Only 80 years later, the first strain gauges based on this effect were developed independently by Evgeny Simon at Caltech and Rug at MIT, both universities in the USA. The latter fixed the measuring wire onto a carrier material, resulting in an independent measuring device for stress and strain. Coil gauges, invented by Eisler, appeared in 1952. Early strain gauges were made of thin wires, then are folded to obtain high sensitivity in one direction, while keeping the total dimensions within classical limits. The transferal sensitivity is smaller, but not important. More popular are the foil gauges, as you can see in this slide. A thin film of conducting material is deposited on an insulating backing material and etched to create a minder-like structure or grid structure. Foil gauges have many advantages over wire gauge. And first of all, because more accurate and cheaper production. The second advantage, better heat dissipation. And the third, final advantage, special construction possible. The sensitivity of a strain gauge is expressed in a relative and resistance change per unit of strain. As you can see, first equation for K here on the top left corner of the slide. K here is called the gauge factor of the strain gauge. Using the general equation for resistance, the relative resistance changes due to positive strain and equals, you can see here second equation, dr over r proportional d rho over rho plus dl over l and minus dA over A. Hence, the change of the resistance is caused by three parameters: the resistivity of the length and the cross-section area A and the wire over field rho. So, in general, all the three parameters change simultaneously upon applying strain. The gauge factor for metal, gauge factor K for metal, can be calculated as follows. When an object is stressed in one direction, it experiences strain not only in this direction, but also in perpendicular direction due to the Poisson effect. Do you agree? Now, when a wire or thin film is stressed in the principal plane, like first of all, it means longitudinal direction, it becomes longer, but also thinner, because its diameter shrinks. The ratio of change in length and diameter is the Poisson ratio, which you may find here on the third equation on this slide. Here it's L is the length of a wire, and R is the radius of the circular cross-section. But you should notice that according to this definition, here is a P is a positive, because dr over d and dl have opposite signs. And the area of a wire with cyclical cross-section is usually equal I a wire is pi times r squared. So if we see another equation for this case, and hence we can find that the next expression for dr over dr, and another expression from which finally the gauge factor results. And we can see here, and we get the final for gauge factor. Okay? So as I said, telling you in the previous lecture, you should not remember all of these expressions, all of this mathematical expression, only to help you more better understanding the physical processes we have in here. Okay? That's nice. Okay. So to find the value for the Poisson ratio, we assume the volume equals A times L of the wire and is unaffected by stress, as we can see from the next expression here, resulting in this expression. So the Poisson ratio in this ideal case, therefore, equals 0.5. For metals of which the strain dependency of the resistivity can be neglected, the gauge factor usually described by this interesting expression. Very simple. K proportion of 1 plus 2 Poisson's ratio. So the gauge factor of a metal strain usually 2. K usually equals 2. In other words, the relative resistance changes equal twice the strain. And you can see this expression here, this demonstrates. And this rule of thumb is only a rough approximation. Be careful. So, first of all, the value of 2 for the Poisson ratio is a theoretical maximum. It means, in practice, the volume will increase somewhat when the wire is stressed. And hence, the Poisson ratio will be less than 0.5. And after that, we may say that the actual values for the gauge factor range is between 0.25 up to 0.35. Further, common strain gauges built from alloy and have a gauge factor larger than 2. And typical values range in this case varies from 2.1 up to 3. And this means that for such material, the stress dependency of the resistivity and cannot be neglected and can be as large as 1.5. The resistivity of a semiconductor material shows a much higher strain dependence, and therefore semiconductor strain gauges have a gauge factor much larger than 2. And this will be discussed a bit later when we will be studying piezo-resistive sensors. The maximum strain of a strain gauge is not large, usually about 10 in power minus 6. For this reason, strain is often expressed in terms of microstrain, or as often telling as a mu strain. 1 mu strain corresponds to a relative change in length of 10 in power minus 6. And secondly, the resistance change is small too, because a strain of 1 mega strain is the strain result in a resistance change only, as you remember, twice times 10 in power minus 6. And the measurement of such small resistance changes will be discussed in the section in one lecture when we study interface. In this table, lists some specification of strain gauges. For comparison, a column for the user-mountable semiconductor strain gauges has been added. It should be noted that these gauges show a considerable nonlinearity. It means even in a balancing bridge, this effect cannot be neglected. And typically for standardized resistance values of strain gauges are as 120, 350, 700, and 1000 ohms. Strain gauges have an intrinsic bandwidth of over 1 MHz. So, the system bandwidth depends mainly on the mechanical interface and readout electronics. The resistance of a strain gauge changes not only with stress, but also with a temperature. Two parameters are important: the temperature coefficient of the resistivity and the thermal expansion coefficient. Both effects must be compensated for because resistance variation due to the stress and possible much smaller, and some changes provoked by temperature variation. The effect on resistivity is minimized by a proper material choice for the strain gauge field of wire. For instance, constantan. This is an alloy of copper and nickel called constantan with a low temperature coefficient. Residual temperature effects due to a non-zero temperature coefficient are further reduced by a proper interface. So, to compensate for thermal expansion, manufacturers supply gauges that can be matched to the material on which the gauges are mounted. It's so-called matched gauges. When free gauges are employed, one should be aware of the difference in thermal expansion coefficient of the gauge and the test material. In this case, the relative resistance change due to temperature effect is expressed, but we will see this next slide in next equation for delta R to R. I just show you for this for a second. Its expression for delta R to R is a proportional alpha T tau times delta T plus difference between alpha S and alpha G times the K delta T. We will be returning this for a bit later. So here alpha is the temperature coefficient of the metal, and alpha S and alpha G are the thermal expansion coefficients for specimen and gauge, respectively. The effect of the different thermal expansion coefficients cannot be distinguished from an applied stress and should therefore be minimized by using matched gauges when large temperature changes might occur. Strain gauges are sensitive not only in the main or axial direction, but also in the transverse direction too. The transverse sensitivity factor Ft, F sub T you can see here in the right equation, and the axial sensitivity Ka is of the order of the few percent and cannot always be neglected. So the factor Ft is determined by the manufacturer using a specified calibration procedure. And in general, a force applied to an object in axial direction generates a biaxial strain field due to the Poisson effect. And the transverse sensitivity of the strain gauge is responsible for an additional resistance change as a result of these transverse strains. If only axial strain has to be measured, the output for resistance change should be corrected for the transverse strain. And this, however, requires knowledge of both the factor Ft and Poisson ratio. And Poisson ratio Va of the object or material. To simplify correction, strain gauge manufacturers specify the overall gauge factor K without any coefficient, based on a calibration with a test piece with a Poisson ratio when equal 0.285, and thus mounted on a material with the same Poisson ratio no correction for transfer sensitivity is needed. And if, on the other hand, the Poisson ratio differs substantially from the value during calibration process, a correction factor, according to this expression, should be applied for the most accurate measurement result. And when both axial and transverse strain have to be determined, a set of two strain gauges can be applied. Manufacturers provide multi-element strain gauges deposited on a single carrier. Other configurations are also available. For instance, a strain gauge rosette, it means 3 gauges making angles of 120 degrees, as you can see here, and 3-element gauge is used when the principal strain axis is not known. From the multiple output of this set of gauges, all strain components of a biaxial strain field, including the shear component, can be calculated. So why we use namely this? The resistance change of strain gauges is measured invariably in a bridge. As you can see here on this slide, we have a typical bridge, right? So the bridge may contain just one, but more often 2 or even 4 active strain gauges, resulting in a half and a full bridge configuration. It may be that half or full, it's in any case for respective. The advantage of a half and full bridge are an effective temperature compensation and a better linearity of the sensitivity. The general expression for the bridge circuit from this slide is given in next equation. You can see in this slide. When in equilibrium, the bridge sensitivity is maximum if all resistance are equal. You may analyze this according to this equation. We consider first the case of 3 fixed resistors and 1 strain gauge, for instance, R2. Assuming that R1 the same as R3 and R4, we measure it simply as R. And accordingly, R2 will be equal proportional R plus delta R, which means that strain gauge has a resistance R at 0 strain. In this case, the bridge output voltage is according to this expression. In this case, the output is 0 as equals 0 at 0 strain. The transfer in this case is nonlinear. Only for small relative resistance changes, the bridge output can be approximated by next expression as a bit here. More simplified. Better bridge behavior is achieved when both R1 and R2 are replaced by strain gauges in such a way that upon loading, one gauge experiences tensile stress and the other experiences compressive stress. Compare the balancing technique as uncertainty after. So, in practice, this can be realized, for instance, in a test piece that depends upon loading. In this case, the gauges are fixed on either side of the bending beam, such that R1 equals R, but minus delta R here, and R2 equals R plus delta R. The resulting bridge output becomes as this expression. The transfer in this case is linear and twice as high compared to the bridge with only one gauge. So it is easy to show that the transfer over 4 gauges of full bridge is doubled again, as you can see by analyzing from this expression here. Why double? Because they have only one part. Without this bi and this part as expression here. So why we have this without 2? Less, and we have this double 2. Also, the temperature sensitivity of a strain gauge element is minimized by the manufacturer, and the remaining temperature coefficient may cause substantial measurement error at small values of the strain. In a bridge configuration, this temperature-induced interference can be partially reduced. And when the gauges have equal gauge factor, equal temperature coefficient, and operate at equal temperature, the temperature sensitivity of the half and full bridge is, as I mentioned, substantially reduced. Reduced compared with a bridge with just a single active element, as you can see. So assume in a half bridge, the two active resistance vary according to R1 equals R minus delta R and plus delta RT, and R2 has the same R plus delta R plus delta RT. Here the delta RS in first is a change due to the strain, and delta RT is a resistance due to the temperature. So the other two resistance values, R3 and R4 equals one each other, and the totally equal R. First part of this. Okay. Right? Okay. So substitution of these values in our equation results in our equation for V naught here. In equilibrium, in this case, delta Rs should be equal to 0. And the output voltage, the offset, is independent of delta RT. And a similar expression applies for the full bridge, if you can see the next equation for the Y naught. So we should be noted here that only the temperature coefficient of the offset is eliminated, but not that of the all bridge sensitivity, which is shown by a rewritten equation for this expression at the bottom and the last one. A condition for adequate temperature compensation is proper mounting of the 2 or 4 active bridge elements. The combined gauges in this figure are very useful, since they guarantee optimal temperature matching. Strain gauges in a differential bridge configuration allow the measurement of very small strain values, down to 0.1 microstrain. The problem of measuring such small strain is actually shifted to the bridge amplifier. Its offset, drift, and low-frequency noise obscure the measurement signal. The way out is modulation. The bridge circuit supply voltage is not a DC, but an AC voltage with fixed amplitude and frequency. In this case, the output is an amplitude-modulated signal with suppressed carrier, which can be amplified without difficulty. Usually it's possibly offset or low-frequency noise from the amplifier and may be removed by a simple high-pass filter. We will be discussed a bit later when we will study uncertainty arc. And demodulation by synchronous detection will yield the original amplified signal. And using this method, strain down to 0.01 microstrain can be measured very easily. Intrinsic shortcomings of strain gauges, like the temperature-dependent sensitivity and non-linearity, can be reduced by dedicated digital signal processing. and manufacturing press of strain gauge measurement, transducers provide signal processing system with the facility. Current research is aiming at the development of integrated circuits in which both analog and digital signal processing are combined, resulting in small size, low cost, and versatile interfaces for strain gauges. For example, 4 different algorithms are compared and evaluated, implemented with analog, mixed, and digital headwire, performing gain and offset compensation and correction. Strain gauges are suitable for the measurement of all kinds of force-related quantities. For example, normal and shear force, pressure, torsion, bending, and stress. Strain gauges respond primarily on a strain, like delta L over L, and using Cook's law, the applied force is found from the value of the compliance or elasticity of material on which the strain gauge is fixed. There are 2 ways strain gauges are applied in practice. And first, mounted directly on the object, whose strain and stress behavior has to be measured. And when cemented properly, the strain of the object is transferred ideally to the strain gauge. For instance, to measure the bending of a robot arm. And second, mounted on a specially designed spring element, like bar, or ring, or yoke, to which the force to be measured can be applied. For instance, to measure stress in driving cables and gyros. So, strain gauges are excellent devices for measurement of force and torque in a mechatronic construction. The unbound gauges are small and can be mounted on almost any part of construction and experiences a mechanical force or moment. Another approach is to include load cells in the construction. A load cell consists of a metal spring element on which strain gauges are cemented. The load is applied to this spring element. This position of the preferably, you can see 4 strain gauges on spring element is chosen such that one pair of gauges is located with compressive stress, and the other pair with tensile stress or differential mode. If the construction does not allow such a configuration, the 2 pairs of strain gauges are mounted in a way that one pair expresses the strain that has been to measure, while the other pair is ideally not affected by the strain. The second pair merely serves for offset stability and temperature compensation. And obviously, the construction of the spring element and the strain gauge arrangement determines the major properties of the device. And this slide shows several designs of spring elements for the measurement of force for various ranges. On the left part of figure A presents a typical construction for large load. The central part of the transducer, you may see here, is a metal bar which reduces cross-sectional area where gauges are mounted. Gauges, all of them as a red color. There are 4 strain gauges in a full bridge configuration. 2 strain gauges, front and back side, measure the axial force, which equals sensitivity. And 2 other gauges measure the transverse force, also with equal sensitivity. So that you can see as a tensile outer, so in inner, it's a compressive. And the same you can see as a compressive part and tensile part. compressing if we have upward direction, and the downward direction is here. We have a tensile. The gauges are arranged in the bridge according to this figure. According to the sequence, R1 is from R2, R3, and R4 as right. The axial position gauge responds to a strain, as you can see from these first equations. The axially positioned gauge and the resistance of the gauge may be changes as proportional as a resistance and changes of the load. So substitution in equation and assuming that the delta R over R is very, very small, much less than Y, after transforming according to this expression, yes, you can see from R1 to delta R2, R3 to R4, and we can find this. So we may get for all our gauges the bridge transfer according to this simple expression. What we may see in this equation, the applied force usually should be found using the Hooke's law, or rewritten in terms of force and deformation. F may be proportional delta L over R times AE. Here A is a cross-sectional area of a bar, and E Young's modulus of material. Or electricity, maybe sometimes using the electricity C. But we should note here that due to the Poisson ratio of the spring element, the compensating strain gauges in the transverse direction contribute significantly to the bridge output. With strain gauges mounted directly on a construction part, the same relation between the bridge output and the force applied. So, in figure B, on the middle of the slide, we have a ring or yoke type spring element. Here the four strain gauges, two inside compressive and two outside tensile, right? And these all four gauges can be mounted in a differential mode. And we now have two compressive and two tensile, right? Which almost equal but opposite sensitivity for the applied force. For this arrangement, full benefit from the advantage of full bridge is achieved, right? Okay, so, and the beam type spring element on the figure C on the right side of the slide allows a differential mode of measurement of the strain as well. And this part allows a differential mode measurement on the strain. Also, two strain gauges are sufficient, one on the top and one on the bottom, and four gauges are preferred to build up a full bridge. Torque measurements are performed in a similar way as axial force measurement. So what will torque? You see, in the left and right, we have different forces applied on the bar. And the strain gauges are positioned on the beam or shaft under angles of 45 degrees relative to the main axis. Yes, do you agree? And you can see these at this position and here on the picture. Again, four gauges are used to complete a full bridge. One pair experience positive strain and the other negative strain, right? So the transfer of a measurement bridge composed of these four gauges. Also, the Marshall position of the shaft is not critical. A close mounting is preferred to ensure equal temperature of the gauges. So, to determine the applied torque or torsion moment, to Tm in Newtonometers from the response of the strain gauges, we use the relation between the torque and shear stress T at the outer surface of the shaft. For a circular solid shaft, this is, as you can see, T shear with D capital, the shaft diameter. But is Hooke's law, and assuming all normal stress components zero, if we have, in case we have pure torsion, in this case, for pure torsion, the bridge output is found to be as this second equation, and namely is second part. And when torque over rotating shaft has to be measured, so conventional wiring of the bridge circuit is not practical. Possible solutions are slip rings or wear sensitive and transformer coupling with coils around the rotating shaft. So a contact-free torque measurement system will be discussed a bit later when we'll be studying optical sensors. Many motion control tasks require both torque and force information, up to all 6 degrees of freedom. Special mechanical spring elements have been designed to simultaneously measure all these components. They are incorporated, for instance, between a link and end effector of the machine. Such end-of-art products are readily available for the market in a variety of shapes, dimensions, down to 15 diameter millimeters, and measurement ranges. A simple design of a force torque sensor consists of a spring element with 6 or even more strain gauges mounted on a spring element of particular shape. A common spring type used for measuring all 6 components is a multi-screw. As you can see from figure A on the left part was a simplified sketch. Here we have wheel-like device is inserted in a robot element, of which torque and force components have to be determined. Each element's end 1 and 2 in left and right side are rigidly connected to the sensor 3. Part 1 to the outer side and part 2 on the hub. On each of 4 poles, 2 pairs of strain gauges are mounted, as you can see on the right part of this figure. When a force or torque is applied to part 2, yes, in this one, of the spaceman, the 8 differential pairs of strain gauges respond in proportion to this quantity, with a sensitivity that depends on the construction of the spring element. Why we have 8? Because we have in and up, that and opposite direction for type, right? So that's right. The gauges are arranged in a bridge configuration for obvious reasons. Each gauge pair responds to more than just one of the components. One of the components X, Fx, X, Fy, Fz, and torque X, Tx, Ty, and Tc. The sensitivity is described by the matrix equation, as you can see here. Very simple matrix equation, right? So here F matrix F is 6 times 1 force matrix torque matrix. As a S is a 1 times 8 strain matrix. If there are 8 strain gauge pairs, and C, you can see here, is 6 times 8 sensitivity matrix or coupling matrix of the spring element. So the force and torque components are calculated using the inverse expression, as we can see from this equation. Inverse expression. Here we say inverse, the coupling matrix. So we should be noting that this inversing strongly depends on the geometry of the spring element and on the position of our strain gauge. Various other mechanical structures have been studied with the objective of combining minimal coupling between the force components with constructive simplicity. For instance, some experiments give an extensive analysis of a 6 degree of freedom force torque sensor, 3 force and 3 torque sensors for a robot gripper. The construction consists of a set of parallel plate beams provided with strain gauges and allows the simultaneous measurement of 3 force and 3 torque components. The total is 6, right? And the force and torque ranges of this combined sensor are 50 Newton and 5 Newton a meter. All of them respectively. Interference or cross-talk errors are around 1%. Using finite element methods, the sensitivity matrix can be calculated and the geometry can be optimized to a minimum coupling of the force-torque components. However, tolerances in the position of the cages and in the geometry of the spring element make calibration of the sensor necessary for accurate measurement of the force and torque vectors. Sensor requirements for application in the consumer market are much less strict compared to those in the previous manufacturer. So, in the precision manufacturing. In recent years, strain gauges have become the typical solution for measuring weight in various economically period household equipment. A typical example is found in bathroom scales, where 4 yokes are mounted at the corners of a plate, each containing 2 strain gauges in half-bridge configuration, as you can see in this figure. These 4 half bridges are connected to a full bridge configuration, and thereby summing the individual contributions to the total weight of the person standing on the plate. In kitchen scales, on the other hand, as you can see here, typically 1 yoke with a full bridge configuration is used. Integrated yokes measuring forces and torques along multiple axes are commonplace in robotic manipulators. The sensors are usually mounted just before the end effector. These sensor systems are highly integrated and have signal processing and acquisition hardware mounted in one single compact unit, as all of these you may see in this slide. Also, in humanoid robotics, such as the IQ project, as you can see in this slide, force torque sensors are used to detect forces on the limb, allowing advanced control strategies like gravity compensation, balancing, and eventually walking. Another subtopic for today's lecture, piezoresistive sensors. Piezoresistive sensors are based on the change in electrical resistivity of a material when this is deformed. Many materials show piezoresistivity, but only those with a high sensitivity are suitable to be applied in sensors. Examples are semiconducting materials and some elastomers. The most popular piezoresistive semiconductor is silicon. Namely, this material can be used as the carrier of the sensor and, moreover, part of the interface electronics, and can be integrated with the sensor on the same carrier. Namely, elastomers can be made piezoresistive by a special treatment, for instance, by adding conductive particles to the non-conducting electrical material. The underlying physical principle of piezoresistivity in silicon goes back to the energy band structure of the silicon atom. An applied mechanical stress will change the band gap. And depending on the direction of the applied force, with respect to the crystal orientation, as you can see here on the bottom, the average mobility of electrons in N-type silicon is reduced, resulting in an increase of the resistivity. So, the gauge factor of N-type silicon is negative and reaches values as high as minus 150. The absolute gauge factor increases with increasing doping concentration. In P silicon, holes are the majority carriers because their mobility is influenced by the position in valence band. And the gauge factor of the P silicon appears to be larger than N silicon. So you may compare as a P-type and N-type of our orientation of silicon. So at the same temperature and doping concentration, and curve P-type have a positive value. So in both cases, the piezoresistive effect dominates the geometric effect as used in metal strain gauges. This table shows numerical values for the gauge factor of P and N doped silicon for three different crystal orientations: 111 here, 110 in middle, and 100 to the right. And a doping level corresponding to resistivity of 1 ohm. And this figure displays these three main crystal orientations of a silicon. Although the resistance change is primarily caused by material deformation, it is common use of express the piezoresistivity of silicon in terms of pressure sensitivity, as you can see from this first equation. With K, the gauge factor by the piezoresistivity that measures in meter per square meter over the Newton, and SAT, the mechanical strain and tension in material. Tension as a T, right? So this is simplified expression because the piezoresistive coefficient depends strongly on the direction of applied force relative to the crystal orientation. The pressure sensitivity pi here of piezoresistive sensor in our silicon depends on three factors, and first of them, the conductivity or orientation dependent. Second, the direction of the applied force. And third, the orientation of the resistors with respect to the crystal orientation. And you know, the second factor in this list is related to the elastic behavior of material, as already described by 6x6 compliance matrix, as you can see in this part. The combined orientation dependent conductivity and compliance yields an expression for the relative resistance change R on the left side as a function of a vector T on the right side. For silicon, many of the matrix elements are zero due to the crystal symmetry, and some are pairwise equal. And this results in the piezoresistivity matrix equation for silicon. So there are only three independent components describing the piezoresistivity in silicon, and their numerical values are given in this table. N-type silicon appears to have a strong negative piezoresistivity, namely in only X direction, and above half as much positive in the Y and Z direction. P silicon is less sensitive in this direction. However, a shear force with respect to an arbitrary direction results in a large resistance change. The unremitting progress in micromachining technology and creation of microelectronic devices, MEMS, very popular abbreviation, have great impact on sensor development. Advantages of this technology are next. All piezoresistors are deposited in one processing step, resulting in almost identical properties. The resistors on the membrane can be configured in a bridge. The resistors have nearly the same temperature due to the high thermal conductivity of silicon. Interface electronics, including further temperature compensation circuits, can be integrated with the sensor bridge on the same substrate. And the dimensions of the device can be extremely small because they are mainly set by the package size and the mechanical interface. So, sensors based on this technology are now widely spread. But much research is still going on to further improve, generally saying, performance. And microelectronic systems, as already mentioned your abbreviation, MEMS, also have their limitations. And other technologies are also being investigated and further developed to create better or cheaper sensors. And this is also a tendency to combine technologies to benefit from advantages provided by each of them. Silicon technology allows the construction of a variety of sensors that make use of the piezoresistive properties of silicon. Examples are pressure and force sensors, accelerometer, and gyroscope. And this figure shows the basic configuration of a silicon pressure sensor and the silicon force sensor, both based on piezoresistive silicon. On the A picture, we have the pressure sensor. On the B, we have a force sensor. The sensor carrier or substrate is a silicon chip. A rectangular part cut from the wafer with thickness about 0.6 millimeters. The wafer material is lightly topped with positive charge carried, resulting in P-type silicon. I hope you remember its advantage. On top of the wafer, a thin layer of N-type silicon is grown, called the epitaxial layer or epilayer. The substrate is locally etched away from the bottom up to the epitaxial layer using selective etching technology. And as a result, is a thin silicon membrane consisting of only the epitaxial layer, the thickness of which is some micrometer. And this membrane acts as a deformable element. Using standard silicon processing technology, piezoresistive sensors are deposited at position on the membrane, where the deformation is greater. The gauge factor of silicon is much larger than that of metal. However, the temperature coefficient of the resistivity is also higher. And therefore, silicon strain sensors are invariably configured on a full bridge arrangement. The silicon piezoresistors are deposited on the crystal surface. So they are technologically bound to a specific orientation. One of the orientation you may see here, as we have already analyzed it, is expression 1 wall Hungary, expression diagonal wall in Hungary 10, and triangle in the bridge 111. So piezoresistors usually have a minder-like elongated shape to obtain the direction sensitivity in a restricted area, as with metal, as compared with metal strain gauge. To optimize sensitivity, the main axis of the resistor should coincide with the direction of maximal piezoresistivity on the membrane surface. The membrane deforms under pressure difference, as you can see from figure A, or on applied force, as on the bottom figure B. Special design allows the measurement of both normal forces and shear force. Independent measurement of the force component is accomplished by proper positioning of a set of piezoresistors on our membrane. You know, a common problem with all these types of sensors is the packaging. Because one of the hands of measuring, like pressure and force, should have good access to the sensitive membrane in order to produce a proper deformation. On the other hand, the silicon chip must be protected against mechanical damage. Another category, as gas pressure sensors, are encapsulated in a small box provided with cold, and that gives the gas access to the membrane, at the same time shielding the chip from the direct mechanical contact with the outside world. And force sensors require mechanical contact between the membrane and the solid object, which is accomplished by a force transmitting structure, for instance, a small steel ball, or a small piece of material fixed in the center of the membrane, sometimes called a mesa or a thin overlayer from an elastic material. Nevertheless, in all cases, this will affect the elastic properties of the membrane. In commercial force sensors, the piezoresistors on the micro machine, the silicon, are configured in a half or full bridge due to the reduced temperature sensitivity and reduced temperature sensitivity. The same technology is used to construct silicon accelerometers and gyroscopes. This figure shows the basic setup of an integrated accelerometer, which consisting of a mass and spring element. All mechanical elements are created in silicon by selective etching. The seismic mass is an isolated part of the substrate obtained by selective etching from the bottom side of the chip. The spring are silicon beams made from the epitaxial layer by etching holes in the membrane, and the mass suspends from the substrate by the thin beam, on top of which the piezoresistive elements are deposited. And when the structure experiences an acceleration in a direction perpendicular to the chip surface, the mass will move up or down due to its inertia. The beam bend and the piezoresistive elements respond to this deformation. Since the device is sensitive to inertial forces, it can be packed in a hermetically closed housing, making it resistant against mechanical and chemical influences from the environment. Silicon accelerometers with micro-machined mass, spring, and integrated piezoresistors feature a high resonance frequency, up to 550 kilograms, and small dimensions and weight up to 0.4 grams and low cost. They are available with 1, 2, or even 3 sensitive axes. Usually can be mounted on a suitable spot on a mechatronic construction, and they furnish useful information on position, orientation, and rotation of mobile parts. The modern technology allows integration of the interface electronics with the sensor body, offering the prospect of very low-cost device. One of the first silicon accelerometers with a complete interface circuit you may see here in this slide. And the rectangular seismic mass is made using bulk micromachining, and the circuit is released in complementary metal oxide semiconductor. semiconductor technology. Micro machine gyroscopes are constructed likewise. They basically consist of a vibrating mass connected by a thin beam by the sensor base. And the micromass usually vibrates in resonance mode, for instance, by an electrostatic drive. And the corresponding bending of the beam is measured in two directions, preferably with 4 piezoresistors in full bridge configuration. Upon rotation of the structure, the suspension undergoes torsion that is measured by piezoresistors integrated in the suspended beam. When the structure rotates, the vibration mode change, resulting in a phase shift of the bridge signal. And examples of such micro-machined angular rate sensors with piezoresistive sensors you may see in this slide. Piezoresistive elastomers are sort of elastomers that are made conductive by impregnation with conductive particles like carbon and silver. The resistivity depends on the concentration of conductive particles, their Marshall distance, and the contact area between touching particles. When the material is pressed, more particles make contact, tending to decrease the resistivity of the material. And the resistance between two adjacent or opposite points of the elastomer layer changes in a nonlinear way with the applied pressure. And here on this diagram, the blue squares present a typical resistance pressure characteristic, revealing that piezoresistive sensors are very sensitive. Because the resistance may change several orders of magnitude, but highly nonlinear, as you can see here. Only one part you may see as linearity, but generally not two. And the initial force is very, very nonlinear, right? The same figure shows the conductance, as you see here. 1 over R ohm has an almost linear relation with the pressure, yes, on the red diamond. A suitable way of creating this reciprocal value is by using a standard inverting amplifier. Besides the nonlinear behavior, unfortunately, most piezoresistive materials show also hysteresis or poor reproducibility, but creep mainly because of permanent position changes of the conductive particles within the elastomer after being compressed or lack of elasticity. The typical behavior of conductive elastomers is still not fully understood, because many attempts have been made to model the piezoresistive properties in relation to composition and manufacturing methods. Despite poor performance of the sensing properties, some useful designs have been constructed and applied for a variety of applications, where accuracy is not an important issue. And namely, this figure shows an example of such an elastometric sensor, illustrating its small dimension, up to the 6 centimeters long. Thickness about the 0.3 up to 0.6 millimeter. So generally less than half millimeter, and flexibility. Piezoresistive sensors are suitable for the measurement of a variety of quantities. The word piezo is derived from the Greek piezon, which means to press. So pressure is an obvious quantity that can be measured by this sensor. However, many other physical quantities can be measured using the piezoresistive effect. A 3D force sensor for biomedical application. Let's a bit study this sort of. So, this sensor has a construction similar to the one shown in this figure. The sensor has a construction as a mainly released in silicon technology. Piezoresistor located at proper place on the square silicon frame, usually 2.3 times 2.3 millimeters, and measures three components of the force from 0 to 2 newtons, applied to a short 1/2 millimeter protruding metal. Evidently, the sensor needs to be packaged in such a way that the externally applied force is properly transferred to the silicon metal, at the same time providing an adequate mechanical and chemical protection. Another application of piezoresistive sensor is the displacement sensor, which is based on a conductive paste deposited onto a piece of rubber. And this high elasticity of the rubber and the paste allows large strain values up to 40%. Its electrical resistance varies also roughly by this amount. As with all sensors based on piezoresistive elastomers, this sensor also exhibits a significant hysteresis. The sensor is designed for measuring the displacement of a soft actuator. For the measurement of body parameters like posture, gesture, and gait, variable sensors are being developed. Ion-based sensors are a good solution for this application, since they can easily be integrated into fabrics for clothing. Suitable sensor materials are piezoresistive polymers, rubbers, and carbon as coating material. Fibers from this material can be interwoven with the textile. Stretching and bending of the textile result in elongation of the fiber and hence a change in resistance. An application example of such variable sensing is given in the next figure, as you can see here. The elongation of the fiber can be as large as 23%, resulting in a resistance change up to 300%. Piezoresistive sensors are also found in inclinometers. Such sensor measures the tilt angle. That is the angle with respect to the Earth's normal. Mounted on a robot, for instance, the sensor provides important data about its vertical orientation, which is of particular interest for walking or ledged robots. One of a micro machine inclinometer was proposed based on silicon piezoresistive sensor. The sensor consists of a micro mouth suspended on thin beam. As you can see, this beam on the middle, and gravity forces of mass to move towards with Earth's center of gravity. And you see the gravitation of the center. And the resulting bending of the beam is measured in two directions by properly positioned integrated piezoresistor. And average sensitivity of this device is about 4.1 millivolts per degree, and over range plus minus 70 degrees of inclination. Resistive sensors based on piezoresistive elastomers can be manufactured as extremely flat devices, which offers a large amount of freedom for design and application. And typically, a sensor can be manufactured using a number of layers of durable plastic coated with the elastomer, combined with flexible tags of a normal conductor. Besides that, measuring linear forces or shear forces for these sensors can also be made into resistive band sensors, And this figure shows a typical resistive band sensor using plastic foil and a resistive elastomer applied in, for instance, a human-computer interface. And these sensors are frequently applied in sensor gloves, so that you might see very popular in some games, playing or some training for disabled people. These resistive elastomers can be used for a variety of sensing tasks in robotics. The pressure sensitivity of the bulk resistance is useful to sense touch, because the high sensitivity for small forces, to measure gripping force and for tactile sensing. The material is shaped in sheets, which is very convenient for the construction, namely of flat sensors, and in particular for tactile sensors. Piezoresistive elastomers belong to the first tactile sensor in robot grippers. They still receive much attention from designers of robots intended for human-like capabilities, in particular soft gripping, like this example. Most resistive tactile sensors are based on some kind of piezoresistive elastomer and can be used for construction of tactile sensors. Many researchers have reported on the usefulness of these so-called force-sensitive resistors as tactile sensors. Not only is the bulk resistivity a proper sensing parameter, but it is also possible to utilize the surface resistivity of such material. The contact resistance between two conductive sheets or between one sheet and the conducting layer changes with pressure, mainly due to an increase of the contact area, as you see on the upper figure. And the resistance pressure characteristic is similar to the C in the bottom. An important aspect of tactile sensors based on resistive sheaths is the selection of readout of the individual pressure points, or taxons. Most popular is the row column readout, accomplished by a line grid of highly conductive electrodes on either side of the elastomer. Elastomer, you can see some column of one and perpendicular row of electrodes, making right angles and thus defining the pressure points of the sensor matrix. And here you see electrical circuit this process. So next lecture we will be continuing study piezoresistive sensors. And for this moment, I think it's enough. I hope you enjoyed this lecture, and I'm looking forward to see you next time. Don't forget, if you have any questions or propositions, you may leave it in our YouTube after this lecture video. Okay, bye. See you next time.